Welcome to this video. This is actually part 3 of the AM modulation and demodulation video series, but this video will talk specifically about the final AM demodulation process, something which I didn't talk about in part 2 and got some fairly forceful feedback that that was something that people wanted to see. So, bowing to your desires for better videos, hopefully this will help. So in the second video, we showed a mixer and a bandpass filter, and the output of that bandpass filter was something that looked like this, and I've called this V sub D for lack of a better thing to call it. This is what the magnitude of the spectrum looks like. I've got bumps at omega IF, my intermediate frequency. And these bumps contain both the carrier, which is now translated to omega IF, as well as the sound information that I would like to retrieve. And so that's what the last step in the demodulation process is, to go from this guy here to an actual sound waveform that I can use. Now, I've shown this in both the frequency domain and the time domain. The reason for that is that there's conceptually at least two different ways to get the original signal back. And the one that's linear is best understood in the frequency domain. And we'll go through this first. It turns out that for AM radio, this is typically not the way it's done because it's more expensive than the nonlinear way, which is cheap. Okay, although when you're using suppressed carrier AM or single sideband or stuff like that, then the approach we'll talk about first in the frequency domain, the linear one, is the one you have to use. So let's go to our picture of the spectrum of the signal as it stands now, and we want to get this all back down to baseband. And so the way that we can do that is we have our signal. Probably you've gotten tired of seeing this, but one way to do this, to move signals around in the frequency domain, is to multiply them by a cosine of the appropriate frequency. Now, I'm going to add a phase term here, and I'll explain in just a minute what this theta is doing and why it has to be there. But so I take this cosine and multiply it by my signal that I'm trying to demodulate, and then I run this through a low-pass filter, and out pops the signal that I was interested in. It still has 1 added to it, but basically it's M of t. Getting rid of the 1 is pretty easy with just a level shifting circuit. Okay, well, let's see if we can figure out how this works. Hopefully you'll recall that if I take in the frequency domain a signal and multiply it by a cosine, or more generally a sinusoid of a given frequency, that it makes a copy and shifts it in both directions. Okay, so I'll have one copy, or we'll do the copy in green even. So I'll have one copy of this bump here shifted down here, and this bump here gets shifted up here to 2 omega IF. And then this bump also gets shifted down here. And this guy gets shifted down here to minus 2 omega IF. So I'll have the green bump at the origin plus the blue bump at the origin. And again, that contains the spectral information of M of t that I want. And so what the low-pass filter will do is I select my cutoff frequency so that it includes the part down here at the origin that I want, but gets rid of these guys out here at 2 omega IF. And to do that, if I've got a good signal coming in here, I don't really need a good or a particularly good low-pass filter to do this. So when I'm done then, after the low-pass filter, In the frequency domain, what I have is my original signal, and since in actual practice this is all done in the time domain, these operations are carried out, this output here really is the signal that I was trying to get. Okay, so that's the concept. Now you need to remember that all of these pictures are magnitude of the spectrum pictures. And so I've sort of cheated, because it turns out that in order for this all to work, I need to know the phase of the sinusoidal part of the signal coming in here. Because if I don't know that phase, when I do the multiplication here, I may or may not be in phase with this signal. If I'm in phase with this signal, then everything works beautifully. If I'm out of phase with this signal, then it turns out the output of my low-pass filter is very close to 0. And that's a bad thing. So in order to make this work, I have to estimate the phase of the signal coming in here. Now, back in the day when the AM radio was first developed, estimating the phase of a signal was a fairly expensive and difficult proposition. And so that's why AM radio is not demodulated this way. In today's world, it turns out that you can buy what's called a phase lock loop chip, and for, in volume, 10 cents a pop, you can estimate this phase and get everything here worked out. But it turns out there's a cheaper alternative that is actually even probably cheaper than, well, actually it's quite a bit cheaper than buying a phase lock loop chip and estimating phase so that you can do this demodulation properly. From the perspective of Fourier transforms, it's nonlinear, which means that it's really difficult to analyze in the frequency domain, which is why I left it off of the series of videos originally, but I've been since chastised, so I won't do that again. Okay, so the cheap way to do this, the nonlinear way to do this, is to look at what happens in the time domain. And again, this is our signal in the time domain. And what I'll do is I'll run this through a circuit that effectively looks like this. It may not actually be implemented like this, but conceptually you can think of it working like this. So this is V sub D, and this is the output, the demodulated time signal that I want. And this, for those of you that are unfamiliar with electronic circuits, this is a diode. And it has the property that it acts like a switch. Whenever the voltage across the diode is positive, it opens up, allows current to flow, and so the voltage drop across the diode will be very small. Whenever the voltage across the diode is negative, then it acts like a switch. It opens up, no current flows through it, or essentially no current flows through it. And so when the voltage on this side of the diode is higher than on this side, nothing flows through here, so it's just the resistor, this resistor and the capacitor working together that cause things to happen. Okay, this diode acts like a half-wave rectifier. And again, conceptually what that means is it takes our signal and just chops off the positive part, or I guess you can say it chops off the negative part and just throws it away. And the positive part gets fed into this resistor and capacitor combination, which is a low-pass filter combination. So again, conceptually, and this is somewhat oversimplifying what actually happens in the circuit, is I chop off these bits down here, and then I low-pass filter what's left. And low-pass filters basically get rid of the stuff that wiggles a lot. So I've got the sine wave that here is wiggling at a frequency of omega IF, it gets rid of the wiggles and just leaves us with the magnitudes. So the output of the low-pass filter is going to look something like this, which tracks pretty closely with our original signal m of t. So, well, actually in this case it'd be 1 plus m of t. And then again, you do some sort of level shifting to get m of t back without the 1, and you're done. So just to give you a little bit more detail about how this circuit works, suppose that at a particular point in time I've got this sort of thing, this sort of wiggly bit going in as VD. Whoops. And what happens is, as long as the input voltage, this VD, is larger than the capacitor voltage, the diode acts like a closed switch, and the capacitor voltage just charges up, or the capacitor charges up as VD increases. So if the red represents the capacitor voltage, it charges up until it gets up to this point, right up here at the peak of the waveform. And then VD starts to go down, which means that the capacitor voltage is now going to be higher than V sub D, which means that this diode then shuts off like a switch. And then the capacitor will start to discharge through this resistor. So I get something that starts to happen like this. And depending on the resistance and capacitance values, that affects how quickly this discharges. Once I get to the point where V sub D is going higher again than the capacitor voltage, the diode turns on, the capacitor charges up until we get to the peak where V sub D starts to decrease. When that happens, the diode turns off, the capacitor starts to discharge through the resistor. So you can see that what this circuit does is it essentially connects the peaks of the waveform. And if my waveform is wiggling quickly enough, which it is in this case, I'm just connecting each of the peaks of my waveform here with my demodulator circuit. Okay, so in the time domain, this is fairly easy to understand. In the frequency domain, this is a mess, because this nonlinear diode does all sorts of crazy things. It turns out that, well, if you have a full wave rectifier, which we don't, the fundamental frequencies that you're working with are doubled. In this case, since we're chopping off the bottom half, we still have more or less the same frequency, but it gets really hard to analyze. In fact, I looked for papers that analyze it and have found very few, and they go into some very complex math and do a lot of very ugly approximation. So anyway, that hopefully makes it clear how we do the demodulation to get back our original signal. And thanks for watching.